Swayam Prabha. Digital India. Educated India.
Welcome to module 8, lecture 2. We will continue with durability of concrete, and in this lecture we will look into frost action and introduce rebar corrosion, reinforcement corrosion. So, essentially we will look at frost action and we will introduce rebar corrosion today. Now, you know frost action of frost usually is more relevant to the cold countries, but in Indian subcontinent, Indian scenario, the Himalayan areas are susceptible to frost action, freezing and thawing, and the problem of freezing and thawing can result in kind of deterioration of concrete. Now, water if present in the concrete can freeze at lower temperature, and you know the ice occupies more volume than the water. Now, presence of this freezing point of water is not fixed unless it is distilled water. We know that depression of freezing point occurs when you have got salts. Presence of salts actually lowers the freezing point, presence of salt lowers the freezing point, salt present lowers the freezing point, all right. Presence of salt lowers the freezing point, and fine pores freezes at lower temperature, right. So, this is one issue. Second issue is, since the porosity, pore sizes differ, salt concentration would differ at different location in the concrete. There is no single freezing point of water in concrete. There is no single freezing point of water in concrete, right. So, therefore, there is no single freezing point of water in concrete. And in gel pores there will be hardly any freezing. So, in gel pores there will be no freezing, no freezing occurs in gel pores. So, what it means, even the concrete is saturated, all and the temperature goes down, freezing will not occur simultaneously in all the pores. Only in some pores freezing will occur depending upon the salt concentration, size of the pore, and of course, how close their proximity to the surface or freezing temperature. Now, when freezing occurs, freezing causes 9% volume increase, and freezing occurs gradually, because all pores will not get water in all the pores will not get frozen in one go. So, there is a 9% volume increase, there is a 9% volume increase. Now, this volume increase actually causes a kind of an excess pressure. So, the water in unfrozen capillary is subjected to hydraulic pressure by this expanding volume of ice. So, what you can look into is something like this. You have the concrete, the aggregates etcetera, and then you have got pores of various kind, interconnected system and so on. The water freezes in some of the pores, the other pores are still free, and the hydraulic pressure in this, hydraulic pressure in this pores would cause an outward pressure onto the concrete, because this is frozen water, this is just water which is unfrozen, and since this is expanding and this is connected, this will actually exert hydraulic pressure in the surrounding concrete matrix. So, as a result there is internal pressure generated. This unrelieved pressure inside induces internal tensile stresses, and there can be local failure. So, there can be local failure could occur, and when thawing occurs again, and when thawing occurs, this old space, for example, if this was your pore space, which actually because of hydraulic pressure cracks occurred in this manner. Now, when actually cracks got expanded or something of this kind. Now, next time when water freezes, water will enter into this as well as into the new cracks, and freezing action will be there in this new cracks, cracked or newly formed fissures or spaces again. So, in other words, now this will exert more hydraulic pressure, this will exert, this will cause more hydraulic pressure into water where there are, this is the water where the pores were. So, this will exert more pressure, because more pore space are available which are filled with ice. So, some spaces which were not earlier filled by water now get filled up by water and can get frozen again, and some portion might get frozen again, and if they get frozen, then that would actually exert a pressure outward, and therefore, this process, the cycle will continue. So, this cycles, as it continues, the process is repeated several times, and then finally, the damage to the concrete will occur. So, that is the action of frost on concrete, this is the action of frost on concrete. So, when there are additional mechanism, when capillary becomes it becomes ice, the vapor pressure reduces. So, when capillary pores, once ice formation had occurred, the vapor pressure will reduce. So, gel water will move to the capillary, So, gel to capillary, because ice has formed here, the ice formation has occurred here. So, here ice has occurred. So, therefore, gel to water will move, from gel to capillary, and then again it will get frozen and the hydraulic pressure will increase. So, this is a kind of a cyclic process, a repetitive process. I mean, it's sort of cascading effect. First, you have some gel formation, some ice formation in some of the capillaries, resulting in excess hydraulic pressure, causes cracking, and next time those crack or fissures that has been created will again filled up by water, and therefore, additional space is now available, more hydraulic pressure, and whenever there is a hydraulic, whenever there is a ice formation in the capillaries, the vapor pressure reduces and gel water moves to the capillaries, and again this freezes, and therefore, kind of a cascading effect, and after number of cycles actually you will find that there is a kind of disruption of the concrete and so on and so forth. Now, the other effect is when liquid water diminishes, concentration of solute also increases, and osmotic pressure increases, adding to hydraulic pressure. So, therefore, concentration of the solute, which changes, basically as we said that solute concentration causes diffusion. We will look into that a little bit more sometime later on, but right now we can just understand this. For example, this phenomena will be something like this. Supposing I have a solute, two tanks, and there is a semi permeable membrane here, and I have got water here, distilled water, and here also distilled water, but with some sort of solution present in this. So, here I have got solution, here the solvent. After some time you will find the concentration tend to be same. After some time you find that after some time one finds the concentration becomes same, concentration becomes same. So, concentration becomes same, concentration becomes same. But supposing I put supposing I put a piston here, instead I put a piston here, I put a piston here, I put a piston here, and apply pressure, it will remain same. The concentration would not change, concentration would not change, concentration does not change if I apply pressure here through a piston. So, this pressure difference is is called this pressure which I have applied implies that there is a pressure difference existing between high concentration to low concentration, and this is called osmotic pressure. This is called osmotic pressure, and due to osmotic pressure solute moves from high concentration to low concentration, high concentration to low concentration. And in fact, it can also be shown that the pressure by concentration is something it is proportional to RT. So, you in fact, pressure by concentration volume 1 by volume is the concentration. So, PV. So, it follows almost the this pressure or sometimes denoted by pi, it follows the gas flow itself, right. So, ideal gas flow itself. So, this can be related so pressure, the osmotic pressure can be related to the gas flow and so on and so forth, right. So, that is what it is. So, osmotic pressure, the solute concentration being different, it can cause actually an osmotic pressure and it can add to the hydraulic pressure. Empty air voids or capillaries when present can relieve this pressure, but supposing I have got empty capillaries or empty voids which is not filled with water, and then when hydrostatic pressure is applied, this get ruptured and the water can enter into this one and this can relieve some of this pressure. So, empty air voids if present in the system, it will cause relieving of the pressure, release of the pressure, and thereby the disruption of the concrete or deterioration of concrete is controlled. So, extent of damage can be surface scaling to complete disintegration as layers of ice are formed initiating from surface and progress through the depth. So, essentially it starts from the surface and penetrates inside, and surface scaling, sometimes constant complete disintegration of the concrete from the surface and so on and so forth. So, after certain number of cycles, certain number of cycles. So, it does not occur in one cycle, first freezing, then thawing. So, more water comes in, next again freezing and disruption and again thawing. So, further more water comes in. After certain number of cycles over the years, actually you find that surface concrete actually is coming out, popping out or something like that, disintegration is occurring. So, that is what is action of frost. If the concrete remains dry, it is not vulnerable to frost action, because RH below 80 to 90% is highly resistant to frost action, because water is not there, what to freeze. So, if the relative humidity is less than 100%, less than 90%, vapor pressure, only vapors will be there and it will not freeze. Since vapors will be there, it will not freeze. So, dry concrete is not vulnerable to frost action, very very important. Dry concrete is not vulnerable to frost action, So, therefore, again we see if we keep water out, everything is fine. If I can keep water out, everything is fine. So, therefore, frost resistance concrete, one way is to keep it dry, but that may not be possible all the time. But what you can do, there was another issue, he said, if there are empty pore space not filled with water, where water can enter during during the freezing to relieve the hydraulic pressure, right, that somehow or other would be able to extend the freezing and thawing number of cycles of freezing and thawing, and the durability of the concrete would increase. In other words, frost resistance of the concrete will increase. So, deliberate air entrainment in low water cement ratio concrete. Now, low water cement ratio concrete will actually allow less water into it, less water ingress, less water ingress. And if I have air entrainment, now what air entrainment will do? It will actually kind of, if this is your concrete, create a sort of isolated small pore system, spherical, well distributed small pore system, air entrainment, air entrain concrete. So, they are well distributed fine pores, but closed pores, well distributed fine pores, but closed pores. Now, these pores initially are dry, not filled with water. Now, once hydraulic pressure inside the capillary is increased, these pore boundaries might get ruptured and water enters there. Now, as the water enters, pressure is released, and therefore, the surrounding concrete remains intact or unaffected. Surrounding concrete remains unaffected. This concrete remains unaffected. This concrete remains unaffected. Concrete here will remain unaffected. So, deliberate air entrainment actually increases the freeze thaw life. Presence of deliberately entrained well distributed air voids adjacent to water filled capillaries allows water to flow into them and relieve pressure. So, that is the idea. Adjacent to the water filled capillaries allows water to flow into them and relieves pressure. So, pressure is relieved actually. So, therefore, the skeleton or the matrix, solid skeleton remains unaffected. So, therefore, it can last, but then the deliberate air entrained voids which are there, once the water enters there, that becomes part of the interconnected pore system. So, next thawing cycle, during the next thawing, the water will penetrate into it, and then again it is also a part of the whole system. But all the air voids will not be filled in one go. So, some will get actually filled in by water, they will come into the permeable or interconnected permeable pore space, but some will still remain for the next cycle and for the next cycle and so on and so forth. So, therefore, number of cycles then air entrained concrete can withstand is much higher than non air entrained concrete, and this can be seen from this diagram. You see, when temperature is going down, this is the lower temperature, lower temperature, low temperature, temperature is lower. There is thermal contraction of the concrete, and if thermal contraction would have continued after 0 degree centigrade, it would have gone like this, parallel to this. But what happens is, if I look at the bulk expansion, look at the bulk behavior, then from this point it starts expanding actually. Why? If it is not air entrained, it starts expanding, because the hydraulic pressure causes the whole thing to hydraulic pressure of the freezing, because of the ice being formed inside, it causes it to sort of excess internal pressure, and that causes a kind of expansion till it fails, till the surface concrete goes out. While if I have air entrained concrete, the pressure is relieved, and as the pressure is relieved, skeleton is it gets contracted because of the thermal contraction effect, and this altogether there is actually a reduction in the volume, even more than thermal contraction. So, it is not only frost resistant air entrained concrete not only exhibit a kind of reduction in a reduction in the thermal contraction effect, but it also shows further reduction in the volume of the whole system, because the pressure that would have been created hydraulically would have been released somewhere else, and the contraction is even more in this particular case. So, additional contraction, this is because of the relief of the hydraulic pressure. This is because of the relief of the hydraulic pressure. So, this hydraulic pressure that gets released, in a way there is no pressure, some pores will be filled with ice, and the contraction of ice will also it will also take place. This all results in volume contraction instead of volume expansion of air entrained concrete. So, that is actually protection from frost attack. Essentially, the effect is loss of surface concrete. Effective thickness then can be reduced when frost attack is occurring, and some sort of empirical formulations are there. So, one can conceive actually with time, this is my section thickness, this is my section thickness. With time, the strength will reduce from the surface to inside. So, this is my design strength at this point F c k, but the strength will be lower with time. So, if it is at very large time or infinite time, h is the, let us say h is the, at infinite time h is the h is the depth up to which the strength reduction occurs, because there is a freezing cycle and thawing cycle. So, moisture will get in during thawing, frozen, and once cooled again, it would some of it will come out. So, finally, the water will again get in. So, there is a wetting drying scenario, and normally there is a depth of influence beyond which no freezing action would be, freezing action of frost action will not be seen. So, effective in this one, therefore, since F c k is only available up to this, in fact, one can conceive that effective thickness is reduced, and some empirical formula is available. There are a number of them, in fact, this is one of them. F c k at a distance d is given by F c k multiplied by 1 minus d by h into n. Now, what is d? D is the depth, and n is n depends upon number of cycles, n depends upon number of cycle, h is the depth of influence, maximum depth. So, when when t is equals to 0, everywhere it will be F c k. So, when t is equals to 0, everywhere it will be F c k. So, this value should turn out to be 0, this value should turn out to be 0, this value should turn out to be 0. So, this value it will be h by d is the depth, and this to the power very large value makes this value altogether small, because this value will be a fraction, d by h is a fraction, 1 minus d by h is also a fraction, and fraction to the power large value would tend to make it very, very small. So, when t is equals to 0, this value will be F c k everywhere. Now, when t is equals to infinity, after very, very long time, this is equals to 0. So, this 0 means this is 0 means this is equals to 1. So, F c k at d, and this is valid up to the depth of h, beyond h this is not valid. So, any depth up to d, this value at t is equals to infinity, this value will tend to be n will tend to be 0. So, this a to anything to the power 0 is equals to 1. So, 1 minus 1 is equals to 0. So, f this value would tend to be at a depth, this will tend to be f 0 only, small, at over a very long period of time, all F c k value will tend to be 0, that is what this equation says. All right, but then this is t is infinity. So, this is one empirical equation through which one can actually get some idea. One can get some idea that this is the how the strength changes. So, this is F c. So, F c would change, Q strength will change like this parabolically in this manner, and one can fit an equation of this kind to this particular one, right. So, that is what it is. So, this is since it is empirical, I have just taken part of it and to explain the scenario. There are similar other empirical model. For example, if you considered rate of R as the rate of disintegration, one can assume step variation like this, step variation like this. So, first cycle, this is the depth of disintegration, this x is the depth of disintegration, this is time. Second cycle there is more, and so on and so forth, and you can actually approximate. So, these are each cycle, every cycle there is some depth of penetration increases, and you can actually linearly fit this. So, depth of penetration can be linearly related to time. In other words, the rate can be, one can find out the rate, which will be slope of this line would be the rate. So, rate is given by another formula, empirical formula, a coefficient called C environmental, C N B, C curing, C age, a constant to the power 0.7, and F C k plus 8 to the power minus 1.4. Now, S is the loss of structurally effective concrete is a function of rate into time. So, rate of structurally effective concrete, loss of structural effective concrete is given by this, which is the slope of this line, and structurally effective. So, this depth represents the depth of disintegration. So, S equals to R into T. Now, how is C environmental, C curing and C age? C environment is related to the environment of exposure, C curing is related to the curing condition, and at age after and these are constants. So, now these are given in the next slide. C curing is given as 0.85 plus 0.17 log D, where D is the curing days. So, you have higher curing days, C curing will be less, in fact, rate will be less. So, you see, you can see the factors which affects the frost attack. C age, so if the age is more, obviously this value should be less, but this will also depend upon the supplementary cementitious material or pozzolanic material that you are using. For example, PSF stands for the proportion of percentage of silica fume, percentage of slag, percentage of fly ash. P etc. are proportion of silica fume, blast furnace slag and fly ash respectively expressed as percentage of mass of total binder content. So, if you use slag, fly ash and silica fume, this effect of age will be less, because this value will be. So, large values of this one, this tends to be smaller value, this 1 minus this higher value, this smaller value. So, this will become 1 minus this. So, this will become larger. So, this has something to do with the effect of age. C environment is given as 80 to 160 for very severe condition, latitude 60 plus minus 5, that is subtropical climate, 40 to 80 for severe latitude, 60 plus minus 10, and 20 to 40 for moderate, and for favorable no freeze thaw. So, depending upon the situation, one can choose this environmental condition. I think this is there is something wrong, this is not correct, this should be 20 possibly. So, whatever it is, so environmental condition, depending upon environmental condition, moderate condition or severe exposure condition or very severe exposure condition, this value of C would depend, and therefore, you can obtain the rate, from this expression. FCK stands for the characteristic strength, 8 is taken as 1.65 sigma. In other words, this represents a kind of mean strength. So, larger the strength, R will be smaller, larger the strength, better the grade of concrete, R will be smaller, and A is a factor, is a constant depending upon S into T is the total time, actually S into T is the time. So, what we have seen is A is a constant depending upon air content. So, you have high air content, there will be a reduction. So, A is a factor or constant depending upon air content, higher the air content, less will be the rate, and therefore, S will be S is, since S is R into T, right. So, R less, that means for loss of structural concrete would be slower process. So, it can last for a longer period of time. So, that is related to frost attack. And surface deterioration by leaching, that occurs in some of those many places exposed to water. So, rate of disintegration for salt weathering situation, is given by again a formula of the similar kind. C, this is an empirical formula, but although the values may not be applicable universally, but it tells us what are the factors which governs this. In other words, in case of cross section, it is governed by the air content A to the power minus 7, the strength of the concrete or grade of the concrete, and it also depends upon environmental curing and age, which again in turn depends upon fly ash, slag, and silica fume content. All right. Similarly, leaching would depend upon C environmental and C curing. The C curing is same as before. Curing, it will depend upon curing age. FC, the formula was, if you can see that, if you can remember, the formula was 0.85 plus 0.17 log of D. So, D is the curing age. So, larger the curing age, C cure is less, right. Larger the curing age, less C cure is less, and so on and so forth. So, C environment is given for the Gulf condition, for marine condition, and for normal condition, this for favorable condition FCK to the power 3.3. So, that means, it is the curing condition is important, same, more the curing condition, C cure will be less. Environment depends upon marine environment, Gulf condition, the leaching, because as you remember, we talked of sea water attack, we said that the ettringite and the calcium sulphate which are formed are leached out. So, this leaching rate is given by this formula, and S gives you the structurally disintegrated concrete R into T. So, this gives us third one is related to abrasion of ice, and a similar sort of situation when there is marine environment or environment where there is water and you have an ice body. So, abrasion depth ABR can be found out. Now, the phenomena is like this, you have a ice comes and hits it, and you have a two-way section, there is a tau acting there, there is a tau acting there, there is a tau acting there, tau shear stress, and also a sigma normal stress. So, both sigma shear stress, because it will hit at an angle, and you will have both shear stress and sigma the normal stress acting onto it, and this causes abrasion of the paste. So, the paste goes out first and then exposes the aggregate, and when we have further shear stress coming and hitting the aggregate and the normal stresses coming and hitting the paste, the aggregate gets loosened. So, loosening of the aggregate would occur, and finally, the aggregate will go out, and then further shear stress and the normal stress will be acting, and this phenomena may continue depending upon how the ice hits, and this scenario this causes aggregate loss and structurally disintegrated concrete. So, S is the movement of ice sheet in kilometer, the formula given is something like this. The depth of abrasion due to ice is given by AI log Ni N2 by Ns by N1 Ri and 1 minus AI into B. So, B is given by this, B is related to strength, S is the movement of ice sheet in kilometer, and N etcetera will just define. So, when an ice comes and hits, the behavior is something like this. So, A is the volume of aggregate proportion of radius r. Now, you see this is in this one Ri, there is a sum I going from 1 to n. So, S A is the volume proportion of aggregate of size r, larger the size, it would depend upon the size, larger the size, and sum total for all sizes should be taken into account. B is related to strength, N is the number of ice impacts, subscript S and L I denotes impact during sheet movement and during loosening of aggregate. So, first is the sheet movement is this first one, S and S in movement in kilometer, Ns and Nl. Ns stands for number of heat during the initial phase, and S stands for later on for loosening, after loosening of the aggregate. S is the kilometer movement of the ice, B is an abrasion rate of aggregate, and ABR is given by this formula. When bond between aggregate and cement has disintegrated under freeze thaw action, ABR could be one part. This was the earlier formula, and this is the case when bond has cement and aggregate has deteriorated under freeze thaw action already. So, that means previous one was before there was no freeze thaw action. but once the freeze thaw action has occurred, this depth of abrasion is given by this this equation, which is more simple. A stands for the aggregate of size, volume proportion of the aggregate of size ith size, and B is of course strength 1 over strength 3 divided by 3.3 divided by strength. So, it is an empirical formula into S. S stands for movement of the ice sheet. So, 3 by F c k into S millimeter per kilometer. So, movement of ice in kilometer. So, that is what it is. So, there is an empirical formula again, gives you abrasion by ice. Now, what are the ways? What are the ways actually what are the ways actually we protect against this kind of scenario? We have seen one is the low water cement ratio, that is strength should be good. Higher the strength, all these cases of frost action, abrasion by ice, etc., or any leaching even in marine environment, this would be less. So, one is the strength. In case of frost action, it is air entrainment. If you have air entrainment, this will perform better. And curing condition, age, etc. So, the factors you have seen. So, protection should be low water cement ratio, air entrainment. Now, air entrainment reduces the strength a little bit, because you are introducing new pores, that will reduce the strength somewhat. Essentially, air entraining admixtures we defined when we talked of admixtures. So, air entraining admixtures can be added, but they would have small action, slight reduction in the strength as well. So, that is the protection against frost action, high water cement ratio, good curing as well as air entrained concrete. Now, let us look into the introduce corrosion. One of the major problem or most common problem is the corrosion of rebar. Rebar corrosion is one of the major problem in RCC, and even in PSC pre-stressed concrete, corrosion is a major problem, and worldwide corrosion is a big problem for metals. A lot of loss or money goes in repair due to corrosion. So, let us define corrosion. First of all, we must understand iron, like we talked of concrete other day, we said that Fe does not exist in nature in isolated form, rather it exists as oxide, sulphide, etc., and in ores. So, in ores minerals, we mine it and extract it. So, the minerals in which iron is contained, they exist in oxides, sulphide, etc., etc. Therefore, iron is not a natural material. Now, how do I get iron out of it? I expend a considerable energy in extracting Fe from ore. Thus, mu chemical potential, that the other day we talked about, mu the chemical potential we talked about, mu of Fe will be higher than Fes, because you have given a lot of energy. So, mu of Fe will be definitely greater than mu of Fes or Fe3O4, etc., magnetite, hematite, whatever you call it. So, you have actually given energy. So, therefore, it will have a tendency to come to a natural state. Hence, Fe has a tendency to react and attain a stable state. Therefore, it has a tendency, thermodynamic tendency, because you have its potential, chemical potential is higher. Reaction of Fe with its environment causes loss of material from structural form where Fe exists. For example, you have a structural steel, corrosion would cause reduction from the steel member, or in case of reinforcement there could be loss of material, but then loss of material might manifest itself in different manner in case of reinforced concrete and in structural system. So, reinforced concrete, it might manifest itself by a kind of expansion, we will come to that later on. So, but loss of Fe with this environment causes loss of the material, it causes loss of the material from the structural form. For example, reinforcement might lose this material, and if this loss of metal, which we are calling as deterioration of the metal, if it leads to impediment of functional performance, that is not able to do the functional performance anymore, that is corrosion. So, therefore, functional performance is important. A little bit of loss of metal if it does not create any problem as far as my functional performance is concerned, I would not call it corrosion in engineering terms. So, when functional performance remains unaffected by reaction, it may not be corrosion in engineering sense. Some loss, very loss, little loss, rate of loss very low, small, slow loss, if that is occurring, I may not call it really a corrosion process. Corrosion process is important when there is a loss in the loss in the functional performance. So, that is how we define corrosion process, that is how we define corrosion process. And if we classify the corrosion, classification can be low temperature or high temperature. Corrosion is generally referred to metal, but then corrosion also exists for many other items, even you might find some book of corrosion of concrete. So, although this is basically deterioration we are talking of, but here we are specifically mentioning about metal, or rather reinforcement or rebar, we are looking at rebar corrosion. So, classification of corrosion in metal can be low temperature corrosion or high temperature corrosion, or you can classify in terms of direct or electrochemical corrosion. Some may be simply oxidized. For example, there is a hot iron high temperature corrosion, you put in oxygen, just blow oxygen over high temperature iron at high temperature, it might get oxidized. So, it is a high temperature corrosion and it is a direct corrosion, but otherwise there can be corrosion which is electrochemical corrosion, but a better way to classify corrosion will be wet corrosion and dry corrosion. So, direct corrosion, dry corrosion is usually maybe direct corrosion, but wet corrosion is largely electrochemical in nature. It is largely electrochemical in nature. It is electrochemical in nature and occurs in presence of liquid. Quite often it is water in aqueous solution or electrolytes, in presence of electrolytes, and this is the most common. So, wet corrosion occurs in presence of liquid, in aqueous solution or electrolytes, and is the most common. And rebar corrosion is wet corrosion in presence of water. Rebar corrosion is wet corrosion in presence of water, because reinforcement is not subjected to high temperature most often, because of cover concrete. Even in case of fire, it takes time for heat to reach there, and oxidation is a secondary aspects, that is not. But within reinforcement, when water penetrates, electrochemical corrosion can occur. So, therefore, rebar corrosion is largely wet corrosion and electrochemical corrosion. So, it is largely wet and electrochemical corrosion, right, largely wet and electrochemical corrosion. Now, to understand corrosion, we might understand what is a galvanic cell. We are familiar with battery. So, this is my zinc shell, dry cell, and this is my graphite or carbon, another electrode. So, there are two electrodes, carbon and this is zinc. Now, if I connect a battery, this is positive terminal, this is negative terminal. So, if I connect a battery through this, what happens is light glows, and we know this the phenomena is electrolysis essentially. Ammonium chloride solution is here, could be if it is or ammonium chloride molten fused form or whatever it could be there. What happens is zinc ion actually moves out of it, right, and basically electron moves in this direction, electron moves along this direction. So, my positive current movement is along this direction, positive current movement is along this direction. So, zinc ion moves along this direction, zinc ion move along this direction, and electron moves along this direction. So, my positive ion current movement is along this direction. So, this is my positive electrode. So, this is my cathode, this is my anode. That is a galvanic cell, we know that. Battery, we use all of them. So, whenever we connect a kind of load to a battery, and this is governed by the the zinc that will get dissolved, the amount of zinc would get dissolved is governed by Faraday's law, which says that mass of the metal dissolved is proportional to current into time or the charge, I into T, that is Coulomb, so that much charge, it will proportional to charge. Now, this constant it can be written as it's in fact, it can be stated in another manner. You need 96500 coulomb, right, or Faraday's constant. So, 96500 coulomb is required to deposit 1 gram equivalent of electrolyte. So, if the metal's atomic weight is m a, its valency or electron that it can lose is z, 2 electrons it can lose. So, therefore, its equivalent gram equivalent will be molecular weight expressed in gram divided by z. So, 96500 coulomb, 96500 coulomb will actually deposit this much coulomb will deposit m a by z. So, 1 coulomb will deposit m a by z into 96500, which is grams, that is Faraday's constant, and IIT coulomb will deposit that many grams. So, this is F, Faraday's constant. So, m a by this is given by, this is the Faraday's law. The mass of metal deposited or metal dissolved, zinc, wood or whatever metal is proportional to the charge you are passing through, or I into T, and it is given by m a divided by z f into I T. So, that is a galvanic cell when you have 2 separate electrodes here. So, that is called a galvanic cell, right, from where you can derive current. A corrosion cell is formed in the same metal, anode and cathodes are formed. If you see this, you have anode and you have cathode. From anode, metal moves along this direction, zinc ion was moving along this direction, and electron was moving along this direction, and at the cathode zinc ion was reaching there and electron was passing in this manner. So, at anode actually metal dissolution occurs, and at cathode of course, other cathodic reaction would occur. So, you can have some negative anode and cathode formation in the metal itself. For example, this is positive, this is positive, this is positive. So, 2 electrodes itself might form in the metal itself, depending upon of course, its composition, because there will be variation in composition. And all metal, for example, if I connect zinc with platinum, zinc and platinum, obviously this will always be cathode. Aluminum with iron, this will be anode, whereas iron with platinum, this will be anode. So, it depends upon the tendency of the metal to lose electron, and this also depends upon its composition, metal or alloy it could be, right, how easily it can lose electrons. So, this we will discuss sometime later on. So, ions positive cathodes and anodes can form in the same metal itself. So, when you are looking at wet corrosion or aqueous corrosion, it is electrochemical, and at anode and cathode can form in the same metal itself, because its composition will differ from point to point, and also the concentration of the electrolyte outside may differ. So, all these factors put together, you cannot have identical kind of a metal or alloy. Supposing you consider a rebar, it will not be exactly same throughout. So, some portion will have a higher tendency to lose electron, some portion will not be. Where it will have tendency to lose electron, that will act like an anode, other places it may look, it may So, at anode actually oxidation occurs and current enter into electrolyte, like I said zinc. At cathode reduction occurs, current enter into the metal, right, current enter into the metal. So, positive ion will enter into the electrolyte, at cathode positive ion will enter into the metal itself. So, here the difference is corrosion cell, you have both anode and cathode in the same metal. Even in same Fe, if you see the outside concentration effect, as I was saying, the metal composition may not be exactly same in this negative zone and positive zone. But supposing I pass nitrogen in the same dilute sodium chloride, ion, 2 ion electrodes are there. I pass air here and I pass nitrogen here, is inert, here oxygen. So, you will find that actually this will act like a, like here it will act like an anode, where and this other place it will act like a. So, positive ion moves out of this one, positive ion moves out of this one, right. In other words, electron moves in this direction. So, this is acting as anode and this is acting as cathode. So, this is acting as anode, where this nitrogen I have passed will act as anode compared to this one. So, it also depends upon concentration of the concentration of the material in the solution. So, this is nitrogenated, I have passed nitrogen from outside. So, that oxygen is driven out, here I pass oxygen and one of them will act, same metal will act like anode and cathode. So, two issues, one, composition of the metals are not same, even concentration of the electrolyte may not be same, and therefore, anode and cathode formation can take place within the metal itself, and that forms a corrosion cell, that forms a corrosion cell. So, differential aeration cell as we call it. So, it forms a corrosion cell. And at the anode or cathode, at the this is the metal, there is an electrical double layer. So, this Helmholtz model, which has been later on. So, the charge, if you see the potential there is a double layer exists, and potential here and in the bulk electrolyte there is a difference. Initially it was conceived as a linearly varying, and the point where it becomes potential does not change anymore, that is called outer Helmholtz plane. But then there is a diffuse layer then conceived called Guo-Chapman model, and then you have got Stern model, there is a diffuse layer which is extending, and then there is a constant. So, basically electrical double layer formation that occurs at the metal. Well, I think we will not go into details of this at the moment, we might come back or discuss this sometime later on. So, basically at the anode metal will come out of this, and metal will come out, and at the cathode actually hydrogen reaction can occur. It is an example, not necessarily always hydrogen reaction will occur, it will depend upon the composition of the electrolyte itself. So, for example, here water is there and reaction of water with oxygen etcetera, if it liberates out hydrogen at the cathode, then two hydrogen can form hydrogen molecule in, let us say, metal in a HCl solution. So, this could be one of the cases where hydrogen evolution is actually occurring, right. So, but metal comes out, metal comes out. So, here the other reaction. So, at the cathode actually H2 will generate, and at the anode metal will get dissolved. So, that shows, and the electron will move like this, that again shows a corrosion cell, aqueous corrosion cell. So, electrochemical metal dissolution, that is what it shows. So, at anode metal gets dissolved and it loses, it becomes ion, loses 2 electron which moves along this direction. At cathode 2 hydrogen accepts electron, and but this is not the all the common reaction. In some cases this occurs, in reinforcement this is not very common, but except in certain cases, we shall see that later on. So, in rebar corrosion, if this is your reinforcement bar, there will be anode somewhere, there will be cathode somewhere, and at anode ion will dissolve, I mean go into the solution Fe2++, electron will move along this direction, and the current flow rate, if I call it density as I core, and at cathode actually this electron will come out, react with water and oxygen to form hydroxyl ion. This hydroxyl ion can further react with this Fe to form FeOH2, which may not be, which is usually not stable and can lead to rust formation depending upon the situation or environmental condition of the electrolyte itself. So, what forms, what kind of rust forms will depend upon the environmental electrolyte condition. Presence of oxygen and moisture therefore is necessary for corrosion reaction to progress in rebar. Completely dry or fully saturated concrete do not exhibit significant rebar corrosion. Being an electrochemical process, concrete resistivity will also play an important role, and we will see this later on. We will come back to corrosion again. So, this is again shows the corrosion process in concrete, but the reaction shown are different reaction actually, hydroxyl ion, then iron, and they together might form Fe2O3, but may form something else also. Let us see the next reaction, anodic reaction is common, cathodic reaction either could be this is there and this may react with the Fe may itself may react with water forming 2 hydrogen and this 2 hydrogen can receive electron and form H2 or Fe can react with FeOH2 or FeOH2 can react with oxygen and water forming FeOH3. So, what we see is there can be different reaction possible. Once there are different reaction possible, FeOH3 can break down into Fe2O3 ferric oxide and water rust. So, there are different kind of reaction and different kind of products are possible. So, different products form or remain stable depending upon electrolytic condition, namely pH or chloride ion concentration, pH or chloride ion concentration. When we are saying depending upon electrolytic condition, the environment, electrolytic environment, mainly it is the pH and chloride ion concentration governs this electrolytic condition. So, different product can form, Now, some product are not so dangerous, for example, in case of chloride there could be some sort of loss in the metal, this reaction can take place, cathodic reaction could be this and then finally Fe plus can react with this. So, if it is chloride is there, without chloride we have seen the reaction and this may form even a kind of pit, FeCl2 creates some kind of rust and finally, some sort of product like this is formed. There are various kind of products formed or shown. We will come back to this sometime later on, but what we are trying to say is depending upon the environment different types of product formation can take place. We refer some condition called passive condition, where it is near to inert condition when corrosion reaction is slow or negligible. At high pH oxides form Fe2O3 or Fe3O4 tends to form a passive layer and protects the rebar. That is why I am saying at high pH Fe3O4 or some black rust as we call it, some products are stable, while at low pH FeOH3 of some form, we will come to that sometime later on, that is stable, which we call as red rust. So, at lower pH high concentration of chloride, passive layer get destroyed and the stable material is and the stable material is, just let me put it, stable material is red rust. Red rust can form. So, you see under different condition different product can form, red rust can form or black rust can form. Now, an analogy is actually the steel, if you look at it, when I produce steel I have created an delta G is the potential difference, free energy I have changed. Now, if black rust is forming it may be very slow rate, if red rusting forming it may be faster rate, and if I have provided a full protection coated it may not, the rate would be very small. So, there all cases there is a tendency of this to come out log T, but the tendency is what we call potential thermodynamic tendency, but the kinetics which governs the rate log T versus the falling rate with log T, rate at which it comes back to the stable state, they might differ. So, in a passive state, depending upon passive state it might be somewhere there, and with a coating, complete coating, protection, 100% no water, almost 0 water, it might be something like this, but in a conducive condition the rate could be higher. So, rate is a function of all this and therefore, tendency cannot be controlled, but kinetics can be controlled. So, service life with respect to corrosion we define, you see concrete initially is passive, but it can lose its passivity, due to pH reduction or chloride coming in from outside. So, therefore, this we call as depassivation time and this is the corrosion time. So, there are two things which causes this are carbonation and chloride. So, therefore, first we will look into carbonation and chloride and then their ingress or their effect, and then we will look into corrosion. So, with this we summarize our discussion. Today we looked into frost attack and the relative models, then we introduced Rebar corrosion and we said that normally it can be passive but carbonation and chloride can actually depassivate it. So, we will start from this slide, last slide that we have just finished in the next class. That is next lecture, module 8. Thank you very much for hearing.